Hello and welcome to the 8.1 lecture. Today we're going to be talking about graphing systems of equations, and this is our last unit in our winter term of flipped algebra 1. So this last unit is all about systems of equations, and more specifically systems of linear equations, just to make it a little bit nicer. A system of linear equations is a set, and I'm going to say a set being like a collection, maybe we'll put it in parentheses, of two or more. Okay, just emphasizing that a set could have one thing, but for us here, this set is going to have two or more linear equations that occur at the same time. Okay, so basically we're looking at two lines at one time. That's really what we're thinking about. Now, the one thing that I do want to emphasize now and re-emphasize and continue to re-emphasize and do it over and over and over again is this one idea that the solution to a system of equations is the point where the two, and I could say the two or more lines cross. Okay, we're going to go over, and you've probably gone over these in the past, so many different ways to solve a system of equations, and we end up losing that idea that we're looking for a point. That's all we're doing. We're just looking for one unique point where these two lines are going to cross. Now, I have one for us to try here and to do it via graphing. The only issue with it is that neither of these are very nice equations. So I'm going to go ahead and put them into slope-intercept form. I'm going to subtract the 3x, and I'm going to divide by 2. And even in doing this to the other one, it's not going to be overly great, but putting it in slope-intercept form will be a little bit easier. So I'm going to graph this one. It starts at 2, and it has a slope of negative 3 over 2. Okay, and I'll just do that a couple times. I can even go the other way. And I'm going to use a straight line here so that we get a good look at where this thing actually lives. If there was ever a time that straight lines were more powerful, I don't know if I'd know it. I think this is the biggest point where straight lines are going to be vital. Okay, then let's do the other one. We'll do the same thing. I'm going to say that this is 3y equals x minus 5. Then I want to divide everything by 3. So we have 1/3 x minus 5/3, which isn't great, but we can still deal with it. 5/3 or minus 5/3 is almost 2. It's 1 2/3. And that's going to be a little bit of a tricky way to deal with my slope, but we can still do it. We're going to go up 1 and over 3. Up 1 and over 3. Can't do it. Go the other way. Down 1 and over 3. Okay, now there is a little bit of estimation that's going on here just by nature of having a point at some number of thirds. And I think that one right there is a little bit low. So we'll go a little bit above that. 2/3 of the way isn't that far down. Okay, but we have our two lines now, and as I said, the solution is going to be where these two lines cross. Now, instinctively, when we're dealing with graphing, there is a little bit of estimation that's happening. I don't know if this point, this true integer grid point is where these two lines cross, but it really looks like it. Let me switch colors on that actually. So this point right here really looks like it. And when graphing, I'm expecting an estimation. Okay, there are so many minor little fluctuations that could happen. I'm going to assume today that any lines that cross do so at true grid points, because overall it still is an estimation. But our answer to this isn't going to be these two lines. It isn't going to be these lines in slope-intercept form. It's literally going to be the point 2, -1. That's my answer to a system of equations, saying that those two things happen at the same time at the point 2, -1. And in fact, that's the only point they have in common. Okay. So now just some steps that you can follow. And we kind of did these steps instinctively. It says to use the graph and check method. So the idea here is that we would graph it, and I did skip the check, but we could do it really quickly. I don't typically enforce this very much. Probably should. I can plug 2 in for x and 1 in for y into both these equations and see if they work out. I guess I'm plugging in -1, aren't I? All right, plugging it in here, I get 3 times 2 is 6, plus -2, which is 4, so it's good there. And then -2 plus 3 times -1 is -2 plus -3, which is -5, so that one's good as well. So that's kind of the check part of that strategy. But anyways, to use the graph and check method, just the 4 steps they give, write each equation in a form that's easy to graph. We did that. We could have graphed it in standard form and looked at the intercepts, but they were somewhat ugly intercepts, even though we kind of dealt with some of the ugliness anyways. Let's see, so write each equation in a form that's easy to graph both of them on the same coordinate plane, estimate the coordinates of intersection, and I'm really good there. Most of the time, I'm going to say, give me a solid guess at where you think those two lines cross. And as long as you have straight lines and they don't veer off any severe amount, you should be able to tell pretty easily. Okay, mainly because of the ones that I picked. Okay, and then it says step 4 is to check the coordinates algebraically by substituting each into the original, into each equation of the original linear system. That's what I did there. Okay, but again, I'm pretty good most of the time. You show me the graph and you go with the point that it looks like they cross at, I'm usually pretty happy with that. Okay, but just to speed things up, I will use, kinda, maybe not. When I can, I will use the intercepts method. So looking at this top one, cover up the x. I get 2y equals 6, which means that y is 3. And then covering up the y, yeah, that's kind of tough, isn't it? Maybe we don't go with that method. So if you don't see what's going to happen there, I'm going to get -6 as an x-intercept. That's a little bit tough to deal with on a graph that only goes to 5 in every direction. If that one's not enough, this bottom one's going to have an x-intercept of 24. Good luck guessing where that is. So let's go ahead and simplify this a little bit. Let's rewrite this one in slope-intercept form. Add the y to both sides. 2y equals, sorry, add the x, not add the y. And divide by 2. So we have 1/2 x plus 3. So plus 3, 1/2 x goes up 1 over 2. Up 1 over 2. Down 1, back 2. Down 1, back 2. And so we do see that my y-intercept or my x-intercept would be -6 right back here. And most of the time it's probably just as good just to leave your lines pointed out like that. I think that that's an okay strategy, but I do like to see that line on there. Okay. Next one. I'm going to subtract the x and divide by 4. I'm going to get -1/4 x plus 6. If you don't believe me, check it. You can figure it out. Still, this one's a little bit tough to deal with, but I know it would be here at 6. I'm not going to put a point there. I'm just going to get a point from my slope and then try to do that again. And I guess I'll run out of room, won't I? So I'm going to sort of guess that it's right here, I guess. Not a very good problem for the graph that I gave you. But it's going to go down 1 and over 4. And look at that. It's going to land right on that other point. So as I graph that line, really it doesn't matter where it really goes because I know that I counted that point twice. Now that point that I'm talking about is this one right here, this 4, 5. So my answer, we're going to call it good at 4, 5. It's always nice when I step my slope out and it hits one of the points that I had stepped out before. Okay, let's look at the next one. I think we can use intercepts method on this one. It's not too bad. Cover up the y. 2x equals -2. That means x equals -1. Cover up the x. -y equals -2. That means y equals +2. Definitely when I'm using my standard form, I really want to graph that line because I only came up with 2 points. If I'm able to step my slope out, then we can talk about, maybe you can get away without graphing the entire line until it becomes an issue. But you got to feel that process out. Covering up the y, we get 4x equals -6, which when we divide by 4, we're going to get -3/2. Okay, so and that's an x-intercept, so -3/2 is really -1.5. And then covering up the x, I get a y-intercept of +6. So kind of trying to guess again where +6 is. And even if I switch it into slope-intercept form, I'm still going to have that +6. So it's still not a great problem for the graph that we have. A line going through those 2 points as best as we can. This one's off to the right a little bit. And I think I'm going to go with that and looking at where they cross as probably right there. And I'm okay with that guess. That is at the point -2, -2. Again, maybe if I switched them into slope-intercept form and stepped my slope out, they would both hit that point. All right, next one we've got y equals -3. So we've got y equals -3, y equals -3. That's no good. Y equals -3 all along here. Sorry, -3. Good call. Good call, good call. And x equals +4. Shouldn't shock you what this answer is going to be. Where are these 2 lines going to cross? They're going to cross right here. What are the coordinates? Oh, x is 4 and y is -3. Just to check our horizontal and vertical line process. But it shouldn't be too bad. And last one on this row here, we have two of them in slope-intercept form, so that's kind of nice. Let's go ahead and put a point at, well, I guess I'll start with the top one. That seems a little bit more standard. Y-intercept at 2, slope of -2. And then a y-intercept of -3 and a slope of -1/3, down 1/3. Hey, look, they share that point in common. I'll bet that's going to be our answer. Because it is, and I know I didn't put any lines on there, but if we quickly throw some lines in there, we will see that in fact they do meet at that point. And again, that point being the answer to our system of equations, 3, -4. Okay, let's let you try a couple. Go ahead and pause the video and give them a shot. Hopefully you had a chance to get that video paused and actually try those problems. I'm going to go over them somewhat quickly and see what we come up with. On the first one, I have an x-intercept of 2. And I cover up the y and divide by 3. For the y-intercept, I have -2y equals 6, so that's a -3y intercept. And we can get that line graphed. Definitely not with the same color. Sometimes the best bet for the straight line tool is start at one point, go through the other, and then drag it back. There we go. And then for the other one, we have a y-intercept of -2 divided by -2 is 1. And an x-intercept of -2. These ones look like they might meet somewhere way down the line. But if I graph that line, it looks like we get a nice solid answer there. Seems to be that point where those two cross. So that's at 4, 3. And last but not least, slope-intercept form. I've got a y-intercept at 3, down 1/2. And a y-intercept of -2, up 2/1. And it looks like I found where my 2 points or where my 2 lines cross without ever graphing a line. So sometimes it matters about how straight of a line you can draw. Sometimes it just works out really nice where it's just based on, yikes, not so much that line, huh? I guess it's not that bad, but I did miss a little. There we go. So it looks like those 2 lines cross right here. And that's the point 2, 2. Okay, so make sure that you get those notes down and get a little summary of what we did today. As far as practice problems go, I think I'm going to be good with odds. And let's say odds on the application as well. So practice. Let's go odds, application. Also odds. Keep in mind that you can find the solutions to the practice problems on the Google Classroom post right below the Mastery Challenge. So if you do those and you want to check your work, feel free to give that a look. Other than that, I hope you have a great day, and we will see you in class.